Hello and welcome to lecture number 10. We are almost a third of the way through the semester. That's crazy. So today's lecture number 10 is on conditional probability and independence. Conditional probability is the idea that sometimes when you're calculating probabilities and you have some additional information, probabilities change. For example, suppose you roll 2 dice and you really need an 11. You're playing Monopoly or some silly game and you really need an 11. So I don't know if you guys are like me as a kid. Sometimes I would roll 1 die, see what it is, and then say, okay, now I need this on the other die and roll it. So I don't know if you ever did that because I was just stupid and, I'm a child. Still am, but so let's say you need an 11. What is, in general, before I roll anything, what is the probability of rolling an 11 when you roll 2 dice? Let's just answer that basic question. What's the probability of rolling an 11 when you roll 2 dice? Well, how many outcomes are there when you're, I'm sorry?
2 out of 36?
2 out of 36. There's only 2 ways of getting an 11, a 6 and a 5 or a 5 and a 6, right? Mm-hmm. So there's 2 ways of getting an 11 and there's 36 possible outcomes, 1, 1, 1, 2, 1, 3, and so on. So there's 2 out of 36 is the probability of getting an 11. But let's say I look at the first die and I see a 3. Because the second die, it rolled off the table. So I haven't had a chance to look at it yet, but I see the first die is a 3. What's the probability of getting an 11 now?
It's 0 now.
It's 0 now. There's not going to happen, right? So having some additional information changed the probability. This is what is called conditional probability, when you're calculating one thing on the condition of something else. And we're going to make it very rigorous, and we're going to add some formulas. But let's do it in the context of some examples. So let's look. I'm gonna spotlight myself so it's a little bigger.
I could send a bullet in the future. Now it's gonna catch it in time.
Interesting. This is better than math class. This is talking about bullets in the future. Is that what I heard?
Yep.
I want to hear this.
I think he's giving an example of what's the probability of him catching a bullet.
If it's Bruce Lee, then maybe it's not 0, but pretty much anyone else, it's going to be 0. And I think even Bruce Lee will be 0. We are on slide number 5 now. I posted it on Canvas. We finished 4 last time. We're on 5. By the way, somebody was asking me about the first test. I kind of looked at the various sections that are coming up, and I saw that after section 6, it's a nice conceptual break. So I decided that we're going to have a test after section 6. So because today is Monday, 6 is going to be on today's Wednesday. 6 is going to be on Monday. And what I decided to do then is give you the exam over the weekend following. So you'll have, 24, 48 hours, whatever to do it. Not start to finish, but you'll have an interval of time where you can take it. And once you start it, you'll have something like 2 hours, whatever the case may be. But it'll be after chapter 6. So that's the plan right now. 6 is a nice little break. Okay?
Wait, Professor, is it still one question?
Is what still one question?
The quizzes. You know how the first quiz is just one?
Yeah, the quiz will be 1 or 2 questions. But I'm talking about the first exam. Right? I'm talking
about.
Oh,
got it. Thank you.
Okay, anyway, so let's look now on the first slide. Conditional probability and independence. So we have a group activity, which we're going to do as a group, I guess. It says, to assess their understanding of probability, a researcher gave the following problem to a group of 4th graders. 10 of the girls in a kingdom are princesses, and 30 are regular girls. Now, I don't like the term regular girls. I think we're all special in our own way. So let's say 10 of them are princesses, and 40 of them are just not princesses, or 30 of them, whatever number it is, 30 of them. I don't like regular. So every time we see the word regular, we'll just translate it in our minds to a non-princess, okay? Because everyone's special. Now, all of the princesses are wearing a crown, but so are half of the non-princesses. They're also, half of them are wearing crowns. Now, suppose that you see a girl from a distance, and that girl is wearing a crown. Is it more likely that she is a princess, or is it more likely that she is a non-princess? That's the question. So, A, here are some answers given by the children. Which children appear to be thinking correctly about the situation? So 1, it's more likely to be a princess because every single princess wears a crown. That's what the first one says. The second one says it's more likely to be a princess because I think it's a princess because it's more likely for a princess to be wearing a crown than for a non-princess to be wearing a crown. The third one says, oh, it's a princess because I really want to see a princess. Now, we all really want to see princesses. I get that, okay? But I don't think it's a very mathematical answer. Question 4, I think it's a non-princess because the number of non-princesses wearing crowns is greater than the number of princesses wearing crowns. And finally, the last one says, I think it's a non-princess because there's more non-princesses than there are princesses. So these are the 5 answers to the question. So what I'm going to do, and I think I actually have it up here already from my class yesterday. So we have a situation, right? There's 10 princesses, and each princess is wearing a crown, correct? So there's 10 crowns for the princesses. Do we agree?
Mm-hmm.
And there's 30 non-princesses, 30 regulars. Well, I'll just use that term because the book uses that term. 30 regulars, 15 of which are wearing crowns.
Mm-hmm.
So in general, we have 40 girls that are in this kingdom and 25 crowns. Those are just the totals. Do we agree?
Mm-hmm.
Now, because you see a crown, how many of those 40 girls do you really care about for the remainder of this problem?
40 minus 15.
25, right?
So what's the answer again?
25.
25. The only ones you care about for this problem are the 25 that are wearing crowns.
Mm-hmm.
You have additional information which allows you to remove from consideration the non-crown wearing ones, right?
Mm-hmm.
Of those 25, which are equally likely to be a princess or a non-princess, how many of those 25 are princesses?
10.
10. And how many of those 25 are non-princesses?
15.
15. So is it more likely to be a princess or a non-princess?
Non-princess.
It's more likely to be a non-princess. Not because there's more of one than the other, because there's more of them wearing crowns
Mm-hmm.
than there are of the princesses wearing crowns. It all comes down to of the ones wearing crowns. Why? Because that is the additional information that you were provided. So when it comes to calculating probabilities, it's conditioned on the fact that you're wearing a crown, and therefore we only care about those ones that are wearing crowns.
Mm-hmm.
So what we're going to do now is we're going to turn to slide number 3, and we're going to answer some questions based upon the information provided. And we're going to first introduce a new notation. So the princess situation requires reasoning about conditional probability. And the notation that's used for conditional probability is the probability of A given B. That vertical line stands for the word given. In other words, you are only considering those individuals that have already satisfied to the right of that line, that have already satisfied B. We don't care about the ones that haven't. Of the ones that satisfied B, the question is, what's the probability of also satisfying A? Let's see it in action, so to be a little less abstract. Okay, so, for example, if one of the girls in the kingdom is selected at random, what is the probability that she is wearing a crown given that she is a regular girl. So because it's given that she's a regular girl, how many of those 40 do we care about for this particular question?
15.
No. Remember,
30.
30.
30.
30. Because she's a regular girl, we only care about the 30 regular girls,
Mm-hmm.
right? That is the consideration for this problem, right? The 30 regular girls, correct?
Yes.
Now, of those 30, how many of those 30 are wearing crowns?
15.
And that's why the probability of wearing a crown, given that she's a regular girl, is 15 out of 30.
Got
Because
it.
of the 30 regular girls, 15 of them are wearing crowns. Does that make sense?
Yep.
Yes.
Okay, I didn't spotlight for a second, but it is now. Let's look at the next one. What is the probability that she is wearing a crown given that she is a princess?
10
out of 30?
Well, remember, it's given that she's a princess.
Wouldn't
what
it
do we
be
care
10 out of
about?
10.
10 out of 10.
10 out of 10, 100%.
It's 100%, right? The likelihood that she's wearing a crown given that she's a princess is 100%, because for this particular problem, the given is princess, so we only care about the 10 princesses. Nothing else matters. And of those 10 princesses, 10 of them are wearing crowns. So 10 out of 10 are 100%. Correct?
Right.
So, sorry, that one I
Yeah.
kind of I don't
So
really understand. Because the
okay.
wearing a crown, I was looking at the 25.
no. But you got to start on the right. You got to start with your given. Given a princess. So
How many of the princesses are wearing the crown?
How many of the princesses are wearing crowns? Yes, 10 out of 10, right?
Right.
Of the
Okay.
10 princesses, 10 of them are wearing crowns.
Okay.
Okay, does that make sense?
Mm-hmm.
Let's look at the next one. What's the probability that she is a princess given that she's wearing a crown? So first, how many of them are wearing crowns?
25.
25.
25. Of those 25, how many are princesses?
10.
10.
But what's the probability?
10 out of 25.
10 out of
10
25.
out of 25. And finally, the last one. The probability that she's a regular girl given that she's wearing a crown. So the given is wearing a crown. How many crowns are there?
25.
25. Of those 25, how many are regulars?
15.
5 out of
15.
25?
Sorry?
15, sorry.
15. So there's 15 out of 25, correct?
Yes.
Does that make sense, this idea of conditional probability?
Yes.
Okay, so just to recap, for those who maybe didn't fully get it, in a regular probability question, you look at every possibility. In a conditional probability question, you only look at those possibilities that are in the condition. And nothing else matters for that particular problem. Okay? So let's now turn.
So sorry, just to
Yes.
clarify, it was
Yeah.
10 out of 10 and then 10 out of 25 and then 15 out of 25?
Yes.
Okay.
So let's now turn to slide number 4 and look at an old situation that we're familiar with, which is the 2 dice example. You know, we've been using this example since day 1, right? We love the 2 dice example, right? It's a wonderful example. So don't shout out the answer. I want everyone to think about these just for a little bit. But what is the probability of a sum of 6 given that it's doubles? And I don't want you to reduce anything to lowest terms. So think about it. The probability of getting a sum of 6 given that you have doubles.
Would it be 1 over 36?
Well, what is your given here?
Doubles.
How many ways are there of getting doubles?
Oh, okay. I got it. I got you now.
So what is it? So tell me the answer. What is it?
1 out of 6.
1 out of 6. Right? Of the 6, sorry, Brooke, was your hand up?
Yeah, I was just going to say 1 out of 6.
Yeah, go ahead. Just shout it out because I only see 6 pictures at a time. So people hands up I can't always see. So
okay.
if you have it, just say it. So there's 6 ways of getting doubles. Of those 6 ways, only one of them gives me a sum of 6. So 1 out of 6. How about reverse it? What's the probability of getting doubles given that the sum is 6?
1 out of 5.
5.
Excellent. 1 out of 5. You all see why?
Mm-hmm.
Because there's 5 ways of getting a sum of a 6, one of which gives me doubles. I love it. Now, the next one is not a conditional. The next one is a straight up. What is the probability of a doubles and getting a sum of 6? So what's my denominator going to be? Even before I worry about the numerator, what's my denominator?
36.
36, because we're looking at everything here. Right?
Mm-hmm.
There's no conditional, so it's over 36. The question is, what over 36? We want
1.
a doubles, beautiful, doubles and a sum of 6. Only one way to get a doubles and a sum of 6, right?
Mm-hmm.
And that's by getting what?
A 3 and a 3.
A 3 and a 3. One way, so 1 out of 36. Beautiful, fantastic. Next one, again, probability of doubles or a sum of 6. First, what's my denominator going to be?
36?
36. Again, this is the whole universe, right? This is no condition here. So the denominator is 36. The question is, what's the likelihood of getting doubles or sum of 6? What is the numerator going to be? For
6.
doubles or sum of 6. What do you think it is?
10?
36.
Wait.
11.
Hold on.
Wouldn't it be 6?
Hold on. I heard lots of answers. Someone said 36 for the numerator. Were you saying for the numerator 36? Anyone? I want to correct misunderstandings.
Isn't
I
the
heard-
denominator 36?
There's no question the denominator is 36 because we're
Okay.
looking
I
at
said
everything.
6 for the numerator.
Huh?
Would it be 6 for the numerator?
Well, let's take a look. Let's take a look. I definitely heard the correct answer. But I also heard some wrong answers. So we want doubles or the sum of 6. First, how many ways are there of getting doubles?
6.
6. How many ways are there of getting a sum of a 6?
5.
5. And if you add those together, you get 11, correct?
Yes, but
But, what's the but?
you're double counting 3 and 3.
You're double counting the 3 and 3. You counted it both in the doubles category and in the sum of 6 category, which means you have to remove that from consideration. So what should your final answer be for the numerator?
10.
10.
So 10 out of 36, which of course you would reduce, but for now it's 10 out of 36.
Hey,
Next,
I'm confused. Are we on the doubles or sum of 6 or the and sum of 6?
doubles or sum of 6, correct. Trying to see who else is. So how many ways are there of getting doubles?
6.
6.
And how many ways are there of getting a sum of a 6?
5.
We're doing the same one over again because someone had a question. 5, right?
5, yeah.
For a total of 11, correct?
Yes.
Okay, but one of them was counted twice because one of them was counted both for the sum of 6 and for the doubles. So we remove it because we counted it twice. So 11 drops to 10. So the answer is 10 out of 36.
So
Make
Professor,
sense? Yeah?
Professor,
Yeah.
when it says doubles, it doesn't necessarily mean the doubles of 6, right? It means doubles in general.
Doubles in general.
Okay, that
Double.
was what
Yeah.
was confusing me.
Yeah, doubles or sum of 6. Two different things,
Okay.
which unfortunately have an overlap, right? Because they have an overlap, we have to remove it from consideration.
Okay.
The next one, what is the probability of getting doubles given that your sum was 7?
0.
0. Because if I'm given that I got a 7, there's no way it could have been doubles.
What would that be over?
Well, it'll be over 6 because there's 6 ways of getting a 7,
Okay.
right? But 0 over anything is 0, so it doesn't really make a difference. But for completeness sake, I would write 0 over 6 because there are 6 ways of getting a 7, none of which give me a doubles.
So Professor, for this one
Yeah.
would, the doubles would refer to 7.
No, the
Right.
doubles is just doubles. They're completely separate things. Doubles and sum of 7 are two different things. Okay? How many ways are there of getting a sum of a 7?
Oh, I see.
6.
Okay.
6. Of those 6 ways, how many of them are doubles?
0.
0. Does that make sense?
Yeah.
Okay. And the last one, the probability of doubles or a sum of 7. First of all, what's the denominator going to be here?
36.
36. We're dealing with everything. And of those 36, how many ways are there possible of getting either doubles or a sum of 7?
12.
12. Is there any overlap that we have to worry about here?
No.
No.
No. So 6 ways of getting doubles, 6 ways of getting a sum of 7. 6 plus 6 is 12. That's the problem. Does that make sense, everyone?
Yeah.
What was the one before that? Sorry.
You tell me. Of the 6 ways of getting a sum of 7, how many of them give you doubles? Of the 6 ways where the sum is 7, how many of them give you doubles?
0.
0.
Okay.
So it's going to be 0 over 6. Make sense?
Yes, thank you.
Okay. So now let's turn to the next slide. And we don't got to really read the first paragraph, which just kind of summarizes the previous example, but we're going to go to the Titanic example. Everyone loves talking about the Titanic, right?
Yeah.
Because that's when Rose died and all these bad things happened. So
yeah, there was totally room on that door.
there was totally room, but if it was me, I would have kicked Leonardo off anyway, so I can't really blame her. What can I say? I don't like him. Anyways, let's just move on, okay? Let's not talk about what could have been, what might have been, what should have been. Let's just go on. So we have on the Titanic, there's 1,237 adult passengers, of whom 770 died. There were also 86 children aboard, of whom 49 died. Now, there's 2 different types of variables here. There's the died or not died variable, and there's the adult or child variable. And what we can do is we make what's called a 2-way frequency table, 2 ways, this way and this way. One variable is here, one variable is here, one variable is child or adult, one is died or survived. And we make this 2-way frequency table. And we're going to fill it in. Okay, now we can't fill in everything right away because they only gave us 1, 2, 3, 4 numbers. And when I look at this chart, there's 9 squares, there's 9 cells. So let's start with what I know. First thing, it carried 1,237 adult passengers, correct?
Mm-hmm.
So what can I immediately fill in just from that information alone?
The total for adults.
The total for adults. So I go to here, I draw, here's my adult column, here's the total. So I can fill in that the total for the adults is 1,237. Yes, Talar.
Would it be okay if you just kept screen sharing the whole time? I think it's just easier. If not, it's okay.
No, I understand, but I also sometimes want to use my Blackboard, and I want you to see that, and sometimes I want you to see me. I tend to, in this chapter, go back to this, to my annotating a lot. So I'm going to pop back in and out, I think more than I have in the past, but I'm not going to stay there. I hope that's okay.
Yeah, that's fine. Sorry to interrupt.
No, listen, I mean, there's nothing wrong with that at all. Okay, I mean, you're asking because you feel that it will help you learn, and there's nothing wrong with that at all. Okay, it's just teaching wise, I want to use different mediums, different methods, and anyways. So there's 1,237 adult passengers. So here's adult total 1,237. We agree?
Mm-hmm.
Of those 1,237, 770 of them died. So there's 3 cells for died. There's this one, there's this one, and there's this one. Does 770 go in one of those 3?
770 is in the died adult con.
Yeah, of those adult passengers, 770 of them died.
Mm-hmm.
So before I even read any more of this problem, there's another cell that I can fill in. Which cell is it?
Survive.
Survive.
Kids.
No, I can't do kids yet unless I read more.
Subtract 770 from the 1200 number, which is 467.
Right. So I know by process of elimination, in some sense, since someone either died or survived, that must be 467. Agreed?
Mm-hmm.
Now, there were 86 children on board. So where can I put in 86?
And the total?
For child.
Total for child, 86 right here. Of whom 49 died. So what can I fill in?
49 in the child died category.
40, oh, that was horrible.
That's
49.
Morbid.
What was that?
Be morbid.
Yeah, no, that was, no, not that, my drawing. I don't care about the kids. I'm talking about my drawing. It's 120 years ago. They'd all be dead now anyway. Get over it. So,
We were still kids.
so 49 of the 86 died, right?
Yeah.
Meaning how many survived?
37.
37. So 37 survived. And now I can also fill in this one here. How much is this one over here?
504.
504. 504 survived. And how many here?
819.
819. And give me two different ways for getting this one here. Or three different ways, actually, in theory. Give me three different ways of getting this one here.
You can add 504 plus 819, which would
Okay.
give you 1,323.
Okay, that's one way. Add these two numbers. What's another way?
Or you add the total going across the row.
These here?
Yes.
Okay. Is there a third way?
Add the 4 squares in the middle.
Yes, I can add the 4 squares in the middle. That also gives the total amount. Of course, why would I want to add the 4 squares when I already have the numbers here? But in theory, I could. And what do I get? 1323. Do we agree?
Yep.
Okay. Now, the reason why, Talara, it's hard for me to stay on this is because once I start writing, I can't scroll anymore.
Okay.
So if
Yeah,
I
I
want to
understand.
if I want to go to the next one, I have to stop sharing and then scroll down and then come back in, and then all my numbers are gone. So hopefully you wrote all, you know what I'm going to do? I'm going to.
Okay, I wrote it all down.
Yeah, well, I didn't, so I'm going to do this so I can have it in front of me.
Professor?
Yeah.
All the way on top of your screen, I can see a little pencil. I wonder if you started drawing with that, it'll give you like an actual pencil and it'll save it for you. That's what I'm thinking.
You mean this thing here?
Yes. Maybe if you exit out of the Zoom drawing.
Or no, she meant like exit out of annotating on Zoom.
Yeah.
Oh, sorry. Sorry.
Yeah, the
hold on.
preview showed like a pencil.
Oh, I see.
I
Hold
didn't.
on. Sorry, I'm going to do this again. Sorry, I'm a noob. What can I say? So I
Oh,
clicked
that's
it.
annotate. You can go up to tools and you can click annotate. And you can draw directly on the file.
Do I do text?
Click anything for now and it'll pop up the toolbar.
Oh, that's
at
just
the
text.
top.
That's actually writing.
Yeah, so you can get rid of that, but also at the top there's a marker and a pencil type thing where the toolbar popped up.
Oh, here.
Yeah.
Yeah.
And that will save it directly on your PDF.
Oh my God. It like makes like, it's so cool. So I can make any shape I want.
Yes, that one's a pen.
I don't know what that is though. How do I clear this?
You have to click it and delete it.
This is so awesome. So if I do like 35.
It'll stay there. If you save the document that way, it'll save it.
Crazy. Thank you. All right, so let's do this. So 460 set. Okay, what the hell is it doing now? Okay, well that didn't work. Help me. What did I do wrong?
I don't know. It's just like each drawing you make becomes a little picture that you can move around. So it's not like it's writing.
Okay.
But
so
you can do a text box, the T. If you
467
there you go.
and then 700. Well, it's like calligraphy. That's cool. And then 12. It gets thicker and thinner. Oh my God. I don't know what I just did. Oh no, it's moving. Okay. And then I have 37. Uh-oh. Okay, don't do that. And then 49. And then 86. And then 504. 819, and then 1,323. Now, what happens if I stop sharing? If I stop sharing and come back, will it be there?
Yes. So try scrolling up and down. It should stay there.
Where am I doing it?
Like on the actual document, if you scroll up and down to the next page.
Okay, so if I scroll up to the next page.
It should stay there.
It's still there. Awesome. Awesome. Thank you so much.
If you save the document, it'll save what you drew on it.
Awesome. This is amazing. This is crazy talk. Okay. Perfect. Thank you so much. I really appreciate your help. You're teaching me, I'm teaching you. What a collaborative effort. Do I get an A or anyways, okay. So now, next line, it goes, suppose you pick a Titanic passenger at random. Find these probabilities. So first, what is the probability that the person survived?
504.
That can't be a probability because probabilities have to be between 0 and 1.
Oh.
504 right? Over 1323.
Good. So because we're dealing with everything, I always like to start with the denominator because the denominator is always easier. The denominator is who am I considering? And the numerator is, of those under considerations, how many of them give me what I want? So when I say the probability of survived, I'm picking a person at random. There's 1323 that I could have picked from. How many of them survived? Talar?
Wait, why did you pick 5? Oh, never mind. I figured it out. Sorry.
All right, good talk. Okay, good. So,
Sorry.
No, don't apologize for asking a question. Nothing wrong with that. So there's how many, so there's 1323 people, and how many of them survived? 504. So it's 504 over 1323. Do we agree?
Mm-hmm. Yes.
For the next one. So how do I get rid of this? Okay, so it's 504 over 1323. Now, next one. Probability of survived and child.
So
first,
total of all children?
Well, so first, what's the denominator?
86.
No, the denominator.
It's not the total of all children.
504.
The denominator, 1323.
Oh, I thought, okay.
I'm still looking at everyone, right? There's no conditional here, right? So I'm still considering everyone. There's 1323, correct?
Okay.
Now, of those 1323, how many of them survived and were a child?
37?
37. Right? 37 of those 1323 survived and were a child. Do you agree?
Mm-hmm. Yes.
So I do the denominator first. I want to know what I'm considering. I'm considering everyone. And of the ones that I'm considering, how many of them satisfy the condition of being of survived and being a child? 37. How about survived or a child? This one's a little tougher. Survived or a child. So first, what's my denominator going to be?
86?
No, my denominator. Always my denominator first.
1323.
1323. I'm still looking at everyone. There's no conditional yet, so I'm considering everyone. Now, of those 1323, how many of them survived or were a child?
504.
No, 504 is just survived.
53.
86?
Oh, wait, 1 second. How much?
553.
553. Let's give everyone a chance to understand why.
Yeah, why 553?
Well, let's think about it. Wow. That's so cool. Let's think about it. So first, survived. How many ways did a person survive? Not how many ways, but how many of the people
Oh, is it the sum of adult and child?
No, it survived or a child.
It's the total number of children.
1 second.
Dead
1
or
second.
alive.
Well, guys, 1 second. Survived. Just that. How many survived?
504.
504. How many were children?
86.
86 for a total of how much?
590.
590. But you just double counted.
37, yeah. So you subtract it.
Wait, what?
I'm so confused with the double counted.
Hold on.
I'm sorry, I must be stupid because I'm lost.
Okay, hold on. No, first of all, that's not the case. Okay. Second of all, how do I erase? Because I think
You have to click.
Commercial?
I think I did my math
Talking
wrong.
about the commercial?
Okay, let's see where this came from, guys. Survived. Okay, turn the mute on, please. Tomas.
That's not me. I've been on mute.
Oh, I'm sorry. I apologize. I didn't see it. I thought it was you. I'm sorry. I apologize. Whoever it was, please. So, survived. How many people survived?
104.
504. How many were children?
86.
Now, let's see where these numbers came from. It was this one and this one, which made 504. And it was this one and this one. Oh, God damn it. And this one, which made 86, correct?
Yes.
So when I add these two numbers, I'm really adding this, this, and this. Because that's where those numbers came from, right?
Yes.
Well, aren't I double counting by adding these ones twice?
Yes.
So because I counted them twice, I want to remove them. This is like the same thing we did before. 6 plus 5 minus 1. Remember for the dice roll problem? We had 6 ways of getting doubles and 5 ways of getting something, and we had to subtract the overlap, correct?
Mm-hmm.
So this is the same situation where we're subtracting the overlap. Okay, the overlap here is the 37 because we counted 37 twice. We counted it both when we calculated the 504, and we also calculated it or counted it when we calculated the 86. We counted it twice. Because we counted it twice, we have to remove it once so that we only get one of each.
Mm-hmm.
Does that make sense?
Yes.
Yeah.
Yes, no, maybe so? Do we all understand?
Yeah, it makes sense now.
So what's 504 plus 86?
590.
Minus 37?
553.
Oh, so it was 553. I thought the math was off, but it wasn't. Okay, 553. So none of those questions so far, not a single one of those questions so far was a conditional question, which is why all the denominators that we've considered have all been 1323. Right?
Mm-hmm.
Next one. What is the probability that the person was a child given that they survived? So because it's given that they survived, what is my denominator going to be?
86.
86.
Oh.
No, not 86. I'm sorry, not 86. 504. 504. The denominator is the given. The given is survived. How many survived? 504. Now, what I want you to do is I want you to mentally or physically cover the second row, because we're not considering that for this problem. We're only considering the 504 that survived.
Mm-hmm.
Of those 504, how many were children?
37.
37. So the probability of being a child, given that you survived, will be 37 over 504. Now, do the next one on your own. The probability of surviving, given that you're a child. First, start with the denominator. We always start with the denominator first. The denominator should always be what you're considering for that problem. And then you do the numerator second. So what's my denominator going to be here?
86.
86, the number of children. That's my given. I'm given that it's a child. So I only consider the 86 children. And of those 86 children, so all I care about is this column now, nothing else matters. Of those 86 children, how many survived?
37.
37. So the probability of a child, given that it survived, is 37 over 504. But the probability of surviving, given that it was a child, is 37 over 86. We're going to ignore this. I just don't like this question. Very confusing, not really straightforward. But does that make sense so far?
Mm-hmm.
Okay,
Yeah.
This is all about conditional probabilities, is about when you're given some additional information and how you use that additional information to compute probabilities. Now, let me see the following question. If you roll, oh, so there's some texts here. Hold on, chats. What do they say? How is the denominator 504 on the second to last one? Well, let's take a look at the second to last one again. The second to last one has a condition of survived, correct? Yeah?
Yes.
And how many survived?
504.
So we only consider the 504 who survived. That's my given. Does that make sense, Nancy? So is the total that survived of, that's correct. Your given is not looking at what's before the line. Your given is what's after the line. You ignore what's before the line when you're first calculating your denominator. The denominator comes from after the line and only after the line. The word after the line is survived. Nothing about child or adult, just the word survived. How many survived? 504. Once you have that, then you go to the front and you say, okay, of those 504, how many satisfy what's before the line? And the answer is 37, okay? Now, let me ask you the following question. If you roll a die, sorry, make it easier. If you flip a coin, what's the probability that it comes up heads? Fair coin. What's the probability that it comes up heads?
A half.
A half. What's the probability that it rains tomorrow, given that it comes up heads?
Not related or correlated.
That's the whole idea, right? What does one have to do with the other, correct?
Yeah.
They're not correlated. In the language of mathematics, we would say that they are independent. Okay, so independence, which is the subject of this slide and the rest of the chapter, independence is when two events have nothing to do with each other. The occurrence of one does not affect the likelihood of the occurrence of the other. So if I say, what's the likelihood that it's going to rain tomorrow, or rain tomorrow given that my coin is ahead, one does not affect the other. They are independent events. Now, that's an example of a very obvious independent event. We're going to do some examples where it's not so obvious, and we're going to come up with a method of just determining whether or not two events are independent. So let's start on slide 7. It says, and as a picture covering in some words, I don't know what you guys see.
That's good.
That's good. Yeah.
Okay. So it says, sometimes knowing which category a person falls into on one variable can change the likelihood of another variable or of the category that they fell into. For example, the probability that a randomly selected boy is autistic is about 0.0238. This is based upon empirical data from probably the world, okay? The probability that a randomly selected girl is autistic is about 0.0053. So boys are much more likely to be autistic than girls. If I see a child that's autistic, do you think that autism, based upon this data, do you think that autism is independent or associated with whether the child is a boy or a girl? Do you think that there's an association or that there's no association based upon this data? What do you guys think?
Associated.
Sorry?
No association?
Well, if there was no association, then why is there a different likelihood of being autistic if it's a boy than of being autistic if it's a girl?
Would the association be with the boy?
No. The point is that if I'm checking the likelihood that someone's autistic, should there be a difference whether it's a boy or a girl?
According to the data, there is an association because there's a higher probability of boys to have autism than girls.
And therefore, there's a connection.
Yes.
Right? If it was independent, then one would have nothing to do with the other. But here, one does have something to do with the other. If it's a boy, you're more likely to be autistic.
Mm-hmm.
So this is an example of non-independent events, because the likelihood of one actually affects the likelihood of the other, or the occurrence of one affects the likelihood or occurrence of the other. In the second paragraph, on the other hand, we have the following study. Suppose you want to estimate the probability that a teen is carrying a cell phone. Do you think that boys and girls are more or less likely to carry cell phones? So statistical data shows that it's roughly the same. That the likelihood of carrying a cell phone if it's a boy is about the same as the likelihood of carrying a cell phone if it's the girl. And as such, cell phone or non-cell phone is independent of boy or girl, of gender in that case. Okay, does that make sense?
Yeah.
Yes, no, maybe so?
Yeah, it does.
Okay. So, we of course want to make this more rigorous. So let's look at the next slide. This frequency table shows the girls in another kingdom. This is a different kingdom altogether. Okay. We have how many, well, first study this chart for a second. Go ahead and study this chart for a second. So what we have here is how many girls in total?
100.
100. We see that in the bottom right cell.
Mm-hmm.
How many princesses?
10.
10. How many non-princesses?
90.
How many crowns?
60.
60. How many non-crowns?
40.
40. Okay. In theory, these two-way tables are very self-explanatory, correct? In terms of what these quantities are. When it comes to probability, it's a little deeper, but in terms of this, just the idea is basically the same thing. Now, what proportion of princesses are wearing crowns? In other words, if we only look at the princesses, because it's what proportion of princesses?
6 out of 10.
6 out of 10. Do you agree with that?
Yes.
So 6 out of 10 princesses are wearing crowns. And what proportion of regular girls are wearing crowns?
54
out of 90.
Now, mathematically, 54 out of 90 as a decimal is what?
60% or 0.6.
It's also 0.6. Even though the numbers are much different, because of course we have a lot more of them, we see that mathematically the percentages are exactly the same. Correct?
Mhm.
And that's just what the math gives us, right?
Mm-hmm.
So in this particular kingdom, is it more or less likely for a princess to be wearing a crown than for a regular person to be wearing a crown?
No, because it's the same percentage.
Exactly, which means in this particular kingdom, wearing a crown and being a princess are independent because one has no effect on the other. Wearing a crown giving a princess or being a regular girl, the numbers are different because the sizes of the groups are different. But the probabilities are exactly the same.
So what if we had 61%?
No. Okay. So then we're getting into a shady issue or a shady area, which is whether you're looking at a sample or you're looking at the entire population. Because if you're only looking at a sample of the population, a small part, you're not looking at everyone, correct? In that case, you have to consider the possibility that your sample is not going to be perfect because it's just a sample, and a sample is never going to be exactly the same. So that gets into statistics where how close to 0.6 for each one it is, and you get into a lot of math, which we'll get to later in the course, about determining whether or not you can conclude independence or not. We're not there yet. At this level, what we're focusing on is, are they the same or are they not the same? Okay? If they're the same, they're independent. If they're not the same, they're not independent. Okay? Does it make sense so far?
Mm-hmm.
Yeah.
Okay. Now, when the categorical variables actually are independent, like this example that we just showed, this kingdom, as it were, then you'll notice that the segments on a bar chart are proportional. What do I mean by that? How many princesses were there on the previous slide?
10.
10. Of those 10, how many wore crowns?
6.
6, which is why 60% of this bar from 0 to 10 is shaded red. Now, how many regular girls were there in this kingdom?
90.
90. And how many of those 90 wore crowns?
54.
54. So this column is going to be higher because, of course, there's more people, but it's still 60% shaded red. So the amount that's shaded red in each is exactly the same. This is the frequency bar chart where you actually count how many there are. Here on the right, we have what's called a relative frequency bar chart. In a relative frequency bar chart, we count percentages. 60% crowns, 40% non-crowns. 60% crowns, 40% non-crowns. In that case, they're identical. Make sense?
Mm-hmm.
Okay.
What's the name of that bar chart again?
On the left is a frequency bar chart, and on the right is a relative frequency bar chart. For a frequency bar chart, the percentages are the same. And for a relative frequency bar chart, they're identical because it's actually giving us percentages. 60% red or crown, 40% not. 60% crown, 40% not. Okay? We can skip this because we're running out of time. And let's go now to slide number 11. In fact, you know what? I tried to explain this yesterday to them and they were having a lot of trouble. I'm just going to do it via example. So the question is, if you have a two-way frequency table, how can you tell based upon the data whether or not the events are independent? So here's what you do. You go to each row and you look at the number in the cell over the total that's beneath it. What's 25 over 30? Some number, right?
Yeah.
It's some number, right? It's what,
Yeah.
point, 0.83 bar, right? 0.833333, something like that?
Yeah, 0.83 repeating.
Okay. And how about 25 over 60? Is that equal?
0.416 repeating.
So that's not equal, right?
No.
This number over that number and this number over that number have to be equal. If they're not, it's automatically not independent. Also, this number over that and this number over that have to be equal. So across a row, the number in the cell over the total has to equal the number in the cell over a total. That has to go across the entire row. And that has to work for every single row. So let's take a look at this example. In a classic psychology experiment, preschool children were put in a room with a treat. The investigator said they had to leave for 15 minutes, and if they did not eat the treat until he returned, they would be given a second treat, and they can eat both. The researchers discovered later that children who waited were much more likely to be happy and successful as adults. Personally, I don't get that. Me, instant gratification makes me happy. Okay, so I really don't get this, but hey, I'm not a psychologist, so what do I know? Okay. Now, suppose that this experiment is replicated with 4-year-olds to see if there's a relationship between ability to wait and whether the child can successfully count 15 blocks. A whole different experiment. Forget about being happy. Can you wait and can you count to 15? So here are the results. How many children were investigated in this study, by the way?
90.
90.
Of those 90, how many were able to wait?
30.
Okay, how many were able to count?
25. 30.
Well, okay, I didn't mean of those 30. I just mean
Okay. 50.
50, right?
Yeah.
In order to be, for Margarita, this is for independence, not dependence. This is for independence. Okay, so we understand what's going on in the thing. So let's start calculating some probabilities. First of all, what is the probability that the person can count given that they can wait? So first, as always, oh wow, that was amazing. As always, denominator first. What's the denominator for this problem?
Waiting.
Well, I'm not looking for a number. I'm looking for a number.
30.
30, right? Because 30 people can wait.
Oh.
And of those 30 who can wait, how many of them can count?
25.
25. And now, how about this one? The probability that counts given they can't wait. What's my denominator?
60.
How much? 60. And how many of those 60 can count?
25.
25. Are those equal?
No.
No.
They're not, right? They're not equal. How about, and therefore we're already done. We don't got to do the second line, but let's do it anyways for completeness. Go ahead and fill in the second line just for completeness sake. So what's the denominator here?
30.
30.
30. What's the numerator?
5.
5. Excellent. What's the denominator here?
60.
And what's the numerator?
35.
And those are also not equal, correct?
Yeah.
So are these independent categorical variables?
Yes.
Yes.
No.
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 They are not independent. They are dependent. One has an effect on the other. Yes, no, maybe so?
Yes.
Yes, okay. So here's a new one. This table gives all of the accidents with injuries in the city of Los Angeles in 2013 for drivers of the given age 16, age 18, and age 90 plus. Now, I don't know about you, but that last column scares me a little bit. So how many people in total were investigated in this study?
712.
712, right? So we understand the two-way table now and what all these numbers represent. The question is the variable fault or at fault and age of driver independent? Now, personally, it's a good question because young kids are a little more reckless and older people are a little slower on the reflexes. So I can see two reasons why, both of them would be a significant amount at fault. Okay, let's see what the math gives us. We do 73 over 113, 334 over 533, and then 42 over 66. Let's do all of those as decimals because that's easier to compare. What's 73 over 113? And I'm going to put it here in the box just so we can have it. How much is it?
Does it have to be exact or can it be approximate?
0.646. So if you round up, it's 0.65.
Okay, 0.65, let's say. And what's 334 over 533?
0.63.
0.63. And what is 42 over 66?
63 or 64.
64. Okay. And now let's do the second row. What's 40 over 1? Well, I can do it already because they have to add to 100%. So this one has to be 0.35. This one has to be 0.37. And this one has to be 0.38. So what do you say? Are these independent or not independent?
Not.
No. Well, they're not equal, correct?
No.
Okay, but look down here. Are the variables close to being independent?
Yes.
Yeah.
Yes, they are close to being independent, but they're not quite independent. If they were, the numbers across the rows would have to match. 0.65, 0.63, 0.64 are not all equal. 0.35, 0.37, 0.38 are not all equal. But they are close to being independent. Now, do you think your answer would change if a column for age 40 were added to the table?
Maybe.
Well, what do you think? If someone was age 40, do you think that they would be also roughly 65% of them would be at fault for accidents?
Well, if all the other ones are so close, then probably.
Yeah, but remember, people who are young and people who are old are going to be more at fault for two different reasons: inexperience and being old.
Low reflexes.
Right, but someone who's 40, now you own your own car. Now you're in the prime, reaction, and you have experience driving, and you're not gonna floor it every time like you do when you're 18, or at least I stopped when I was like 39. So
Yeah, you have kids and you don't take that many chances either.
Exactly. So there's many reasons why I personally would think that if someone were age 40, then the top number would go down significantly and the bottom number would, of course, go up. But that's what a statistician does, right? They have a hypothesis and they test it, right? They go out there and they say, this is what I think would happen. Let's see what actually does happen.
And insurance companies too.
Well, insurance companies for sure. Insurance companies make their whole living on knowing exactly what percentage of people are going to get into an accident in different demographics. That's how, that's how they make money in the first place. Okay. So let's look at the next example. The table below gives only the marginal totals and the grand total. So how many people suppose you lost all the information. Suppose somehow, you spilled something on your paper and all of the numbers in the cells all went away. And all you have is the stuff in the margins on the right and on the bottom. How many people are we investigating this problem?
100.
100, okay? Suppose someone told you that the variables were independent. Is that enough information for us to fill in all 4 cells? That's the question. If we know that we're talking about independent events, is that enough to fill in all 4 cells?
Probably yes, because it would have to equal.
Okay, so
Yeah.
give me a possible number for these two, and we'll test it.
Well, what I thought would be 35 divided by 2, which would be 17.5. I don't know if that makes sense.
Well,
'cause-
you can't have 17.5 people drinking,
Yeah.
right?
No, you can't.
Right? So give me two numbers just give me any two numbers that might work for these two
20 and
cells.
15.
Sorry, one more time?
20 and 15.
Okay, let's try 20 and 15. Now, first of all, notice that they do add the 35, okay, which is condition number 1, right? These two numbers must add the 35, correct?
Mm-hmm.
Okay, now, 20 over 80 and 15 over 20, are those equal? What's 20 over 80?
25%,
25%. What's 15 over 20?
75%.
Well, those can't be independent then. So those numbers were not correct. This number was a lot smaller than this number, correct?
Right.
This was 25%, this was 75%, right? So I want to make
30.
this number go up and this number go down.
35.
How much?
30 and 5.
Okay, let's try 30 and 5.
Professor,
Yeah.
is this just kind of like a guessing game, or is there an easier
Well,
way
there is a mathematical way of doing it, but I think it's just easier just to guess and check.
to... Okay, thank
But
you.
but if you were really inclined, there is a mathematical way. But my experience with this class, and I mean no offense by this, is that people would rather just guess and check than learn a slightly advanced mathematical method.
Okay,
But
thank you.
but if you want to,
Oh, I
I'm
know.
more than happy to show it to you.
Yeah.
So let's try this. What's 30 over 80?
0.375,
What's 5 over 20?
0.25.
So now we went too far. This number is smaller.
I have an idea.
Yeah.
Couldn't you compare the total for drinks sports over the total and make that proportion the same for the number over 20 and the number over 80?
So you're saying we want both of them to be 35 over 100.
Yes. So could you multiply 20 times 0.35?
And what do you get when you do that? Well, not
7.
20. Where do you get 20 from?
The total for doesn't. So if we have,
Would it be,
you
think you would do 80 times 0.35.
Yes, 80 times 0.35.
And then 20 times 0.65.
No, just what's 20 times, let's do one thing at a time. What's 80 times 0.35?
28.
So 28.
And then 7 because you have 35.
So 28 and then 7, right?
Yeah.
But then I don't got to do it again. This is automatically 13. This is automatically 52.
Yeah, what I was saying is that you take the proportion of the total of 35 that drink sports drinks over 100 people, which is 35%. And if they're independent, then the percentages have to match across the board. So then you can multiply 20 times 0.35 to get the number that drinks sports. And
I understand. I know. I see what you're saying. I'm sorry. Yeah. So I just was pointing out that there was an easier way, because once you have one, you get all the other ones for free.
Okay.
You
Yeah,
see
so
what I'm saying?
I was just saying to do it with the 20, but you started with the 80, so same difference.
Okay. Okay. Yeah. Same thing. Well, let's check. What's 28 over 80?
0.30.
Sorry? I can't- Someone saying something? I can't hear.
0.35.
0.35. And what is 52 over 80? Or sorry, what's 7 over 20?
0.35.
0.35. So they do match, and that's a wonderful way of doing it as well. You recognize that 35 over 100, 0.3. And by the way, when you asked me, was there a mathematical way? I wasn't even thinking about that. I was thinking about something else. So this was a lot better and a lot smarter and just really, really nice. Now, do you think, yeah.
I'm really confused.
About which part?
About how you got 0.35 and...
What's 35 over 100?
Oh, okay. Oh, and so then you just multiplied that by the total?
Multiply that by the total, multiply that by 80, that gives you 28, so this 30 was wrong. And multiply it by 20, that gives you 7, although you didn't need to, because once this is 28, they have to add the 35.
Yeah.
And then once this is 7, this has to be 13, and it has to be 52, and the rest of it comes along to the right. That's exactly it.
Oh my gosh. Okay, thank you, Claire.
Wait. Yes, that would have worked, Solaire.
That's a 35 over 100 equals
Yeah.
x over 20.
Yeah, and that would have given you 7. Exactly. Now, do you think that these two variables actually would be independent in a sample of 100 high school students?
Probably not.
No.
Well, you can always do a study if you want. I don't know. Back in the day when sports drinks first came out, they were for athletes.
Yeah.
Nobody else drank them. They were for athletes. Everyone else drank soda or water or whatever. And nowadays, everyone drinks Propel and they drink Gatorade and they drink there's like a million different things. Anyways, it is 8:15. I will put up the quiz tonight. You'll have 24 hours or so to take it. I'll put it on Canvas. So just look for it tonight or tomorrow. And just take it when you can. I don't even care about 24 hours. Just take it when you can. And I guess I'm going to stop sharing. Can you please post this recording immediately to review? Yes, the problem is that it takes like an hour to process. It has to compile, upload, whatever it is. But as soon as it pops up, I will post it. So it'll be like an hour. Okay. But other than that, we're done for today. So have a wonderful everything, everyone.
Thank you,
And
Professor.
I will see you guys all. Again, look for the quiz. You're welcome. Look for the quiz. Take it when you can. I'll grade
Professor?
it when I can. Yes.
Are we going to email you the answers again, or is it going to be on Canvas this time?
I don't think it'll be on Canvas because I have some ready-made quizzes that are not on Canvas.
Mm-hmm.
In terms of how to get it to me, I think the easiest one that I had was, because people sent the email and people did it on Canvas, sending it to my email, the david.berkowitz@csun.edu, was the best of all the approaches when it came to grading. It was the easiest for me. If you do it one of the other ways, that's fine. But the easiest for me was certainly that email address.
All right, thank you.
Okay. For whatever reason, the format was easier, huh?
Can you repeat the email, please?
I'll type it in.
So you would like us to email you through like our not through Canvas, but to your email directly?
Either way, but for me, the easiest for me to read and to look through happened to be that format for some reason. It was just easier than all the other formats, all the other email addresses. So Larry, you have a question?
Yes. Would you mind posting the quiz now so I can do it before I sleep?
Before you sleep, geez, demanding. Okay, well, tell you. Okay, fine. Let me get it right now. Hold on.
Thank you.
And before you sleep, jeez.
I want to get it out of the way.
Make me sleep better at night, not having that anxiety.
It was
So
chapter. It was chapter 3, right?
Yeah.
All right. Let's find it. Hold on. Yeah, it's only the question you can ask while I'm looking for this. But go ahead.
So would we then have a quiz for chapter 4 next week?
Monday, right?
Yeah, Monday I think we said.
Okay.
But again, it won't be in class, so it'll be
Right, it'll be like the same.
It'll be a similar thing, yeah.
Okay.
Yeah, Professor, when I first emailed you, I first emailed you like the beginning of the semester, from an email that I got on CSUN, and it was not. I saw that you just wrote the right one in the chat, but the one that I had like after your last name it was like .44.
Yeah, that will get to me as well. It's just I just got a new email address at the beginning of the semester, and I'm trying to move everything to that one. So that's the easiest one. I'm looking for the quiz, which I'll post as soon as I find it. Okay. Anyways, as soon as I close this recording, I can start uploading it, and then because it doesn't start.
Bye, Professor.
No. I'm not telling everyone they have to leave. I'm just saying if you're just sticking around just for fun, I'm just saying as soon as we're done, it'll start uploading, and I can do that.
Okay, so
And
good night, Professor.
good night, guys. Okay.
Have a great night and
Good
stay
night,
safe.
guys. I'll see you guys soon. Okay.
Thank you.
Okay, bye-bye.
You want anything, Dave?
No, I'm still teaching that. So, okay.
I just wanted to tell you, make sure you save the file, the preview, like
What
when you
pre-
go out, so all the annotations that you made, they save properly.
Okay, so, yeah, it's too late now.
Oh my god.
But,
I mean, you can hope it's.
but as long as you have them on your end for when you're viewing, that's okay.
Oh, okay. All right.
Okay? All right.
Yeah. Good night.
Good night. Good night. Okay. Okay.